So in this problem, you will be given two numbers, A and B, and you can perform some operations on these numbers. Like you can add 1 in A as many times as you want, and you can perform OR on A with some value X, right? As many times as you want, and X can be choosable by you. Right? You can choose any value. Okay. And similarly, you can do +1 operation on B as many times as you want, but you cannot do OR operations on this, right? And the aim is to make A equal to B, right? By doing these operations, minimal time possible. Like you have to minimize the number of operations and equate A and B, right? So let's break this problem in two parts. Okay. So here if B is less than A or if B is greater than A. Okay, we can include equal to condition also in here. So if B is less than A, then as you can observe, doing +1 or doing OR operation will always increase the value. Okay. So if we do this operation on A, it will increase the value of A. Okay. Which will not help us because we have to increase the value of B, right? So here we will perform operations on B, that is addition operation, right? And what will be the number of operation that we will be performing? That will be equal to A minus B, right? These many times we will perform addition, +1 addition in B, and then it will become equal to A, right? So if this is the scenario, then answer will be this, A minus B, as simple as that, right? Now let's talk about this scenario, right? Scenario number two. This is one, this is two. So let's talk about this. Okay. So uh, in this case, in this case, I can guarantee it that I can convert A to B in only three steps, at max three steps, right? So let me explain you how. So let's take any number. Let's take this one. This is our B, right? And we have our A as this. Okay, this is our A, right? Now, A will be lesser than B always, right? So this was the condition, right? Now, what I will do, I have to convert this into this in three operations, like I have said earlier, right? So, firstly, I will try to make this number, this 100 000 like 1 2 3 4 5 6 7 1 2 3 4 5 6 7. So I will try to make this one. From this, I will try to make this. So how can I do that? Right? So let's do an OR operation on this firstly. So for doing OR operation, I will take three seven ones. Okay, I will take seven ones and zero and do the OR operation with this one. So this is 0 0 1 0 1, and I have seven ones. Okay, and seven ones. 1 1 3 4 5 6 7. This is 0 0. Okay, and here also we have 0 0. Right now, after doing the OR operations, I have 1 1 1 1 1 1 1 0. Right. So I have converted this to this one. Okay. Now if I will do +1, this was the first step, right? If I do +1, it will be converted to 1 0 0, 7 times 0, right? So 3 4 5 6 7, right? So I have made this number, which I was talking about. Like I wanted to make this number. Now this was the second step, right? So I have used two steps to convert this number into this number. Now in next one step, I will convert this number to this number. How? So the number is, so this is the number. If I will do the OR operation with this one, that is 0 0 1 0 0 1 0, then it will become 1001010, which is equal to B, right? So this is the third step. So as you can see, I have converted A into B in three steps, right? So you can use the same technique to convert any number into B, right? Only in three steps. How? You have to just create, you have to just create a number, like you will take the most significant bit of B, and that number you will make from A. So you will make 1000000 initially from A, like A can be anything. You will make this number from A using two steps, and then you can simply perform OR operation with this number, this and this number to make B, right? So I hope you have understood that we can perform, we can convert A to B by only three operations. Okay. So by this condition, we have concluded that if B is greater than A, then the answer will be 3, right? In this case. Now let's think, can our answer be less than 3 also? Can our answer less than 3 also? So now if our answer is 3, if our answer is less than 3, then we have to do only or either two operation or either one operation, right? So if B or A is equal to B in this case, then I can say it will only require one operations. How? So I will just perform the OR operation of A with B, and that will be equal to B, right? So this will take one operation. So I can do this in one operation if B or A is equal to B. So in that case, this will be the answer. The next is, if I will do plus 1 to A and I will OR with some X, and if this becomes equal to 2, then I am doing two operations, right? So answer will be 2. And what are the other ways in which I can only use two operations? So other ways can be, I can do OR with A and plus 1 with B. So this is also taking two operations, right? The other can be, first you will do OR operation, then you will do addition, and it should be equal to B. This is the third case. It is also using two operations, this one and this one, two operations, right? So how can we check that whether this can be done or not? So we can check this by taking X as equal to B in this case and X as equal to B plus 1 in this case, and we can modify this equation as A or X equal to B minus 1, right? So we will take X as B minus 1 in this case, right? So you can think more deeper why we are taking X as B and X as B plus 1 by thinking about this also. So we will always take X as B, or in this case our X, in this case our X will be B minus 1, in this case our X will be B plus 1. So if we are taking X as B plus 1 and this condition holds, then we can say that we can, in two operations, we can make A equal to B, right? So if A or B is equal to B plus 1, then we can say it will take only two operations to make A and B equal. This was the this is second equation, this is first equation, and this is the third equation. So we can convert these also. So similarly, A plus 1 or B is equal to B, then we can also say it will require two operation, and here we can put B minus 1. Sorry, here we will be putting B plus 1, right? So this will be B plus 1. Now here we can put a, or in the place of x we can put b minus 1. If this is equal to b minus 1, then we can say that we can equate a and b in two operations, right? So finally we are remaining with these four conditions. One is here, this is the first one, this is the second one, this is the third one, this is the fourth one. So we have to check for these condition also. So let's code this problem, right? So as you can see, we have test cases here. So I will take t and the value of test cases, right? Then we will run a while loop 3 times, and here we have two values, and the value can be 10 to power 18. So we will take long long. Then we will take the input, right? Now, as we have discussed, if b is less than or equal to a, we can print the answer will be a minus b, right? And we can continue. But if it is not the case, then our answer will be minimum of 3. Like as I have discussed, I can convert a to b at most 3 operations, right? Uh, and it can be b minus a also, right? So the minimum of 3 and b minus a, right? And here, since b and a are long long, so I have also I have to take 3 also as long long, right? Now here the next thing is we have to check if a or b is equal to b, then we will be having answer is equal to minimum of answer comma 1. Like this is the first condition, right? Now the second condition is if a or b plus 1 equal to b plus 1, then we can say answer is equal to minimum of answer comma 2, right? So this was the second condition. Like in if this condition is followed, then the answer will be 2, right? And the next is this condition. So if a, what was the condition? A plus 1 or b, right? A plus 1 or b is equal to b, right? Then our answer will be equal to minimum of answer comma 2. Okay. And if the last condition is a or b minus 1 equal to b minus 1, right? So a or b minus 1, if this is equal to b minus 1, then we can again say that answer will be equal to minimum of current answer or 2, right? Now let's put this equation into else. Okay, now you will print the answer here. Okay, so I think this will be correct. Let's check this. Okay, there is a problem on 27th line. So here um, we have to place one more bracket here. So yeah, it's working as you can see. So yeah, that was the solution. I hope you have understood that problem. Yeah, thank you.
Hi everyone, in this video we'll be discussing the video editorial for the problem split the array. In this particular question, what you'll be given is, you'll be given an array of length n. So basically you'll be having an array that will be of length n, so it will have n elements inside it. After this, what you have to do is, you can split this given array into non-empty subarrays, right? So you have to split this particular given array into non-empty consecutive subarrays. You have to split it in some subarrays, and different subarrays can have different lengths, right? So there can be, let's say, one of the subarrays can be of length 3, then another subarray can be of length 4, depending on the situation, right? So the subarrays, different subarrays can have different length, and every element in the array should be included in exactly one of the subarray. So suppose that there's one element, let's say there is one element, the ith element is ai. So this particular element should be included in exactly one of those subarrays, right? It cannot be included in multiple subarrays. This is also something that you have to take care of. Now the question says that if the ith element is at the jth position in the kth subarray, so if suppose that this was the ith element in the array, right? So if the ith element in the array was ai, and suppose it is at the jth position in the kth subarray, right? So what you will be doing is, if it is in the position jth position in the kth subarray, then it will add this much beauty to the array, and the beauty that it will be adding to the array is minus 1 to the power j plus k mod 2 into a of I, right? So this is the beauty that it will be adding. So basically, if the aith element is present in the j at the jth position in the kth array, so the beauty that it will be adding is -1 to the power j plus k modulus 2 into a of I. So this will be the beauty that it will be adding. So what is your task? The task in this particular question, the task that you have to do in this particular question is that for every given array A, which is of length n, you have to find the maximum beauty obtained by optimally partitioning, right? So you have to partition this given array optimally in such a way that you obtain the maximum beauty after doing the partitions, right? So that is what you have to do. And let's read the input format. So in the input format, basically you will be given t test cases. That is, for each test case, you will be given an value n, that is the number of elements in the given array, and you'll be given all the elements of the array, right? So your task is to print the maximum beauty for all the given arrays, for all the given t test cases for a particular case, right? So if this is the case, then this will be the beauty. They have explained it, so I hope that you must have read this particular explanation. It's very clear to understand. Now in this particular question, what we will be doing is, first of all, we know that this is how it's done, right? We have understood the question completely. Now the thing is that we can understand that we have to apply some kind of optimization approach in this particular problem. So what we can do is, we can make dp of we can declare a dp of which will be of size, which will be having indexes of the elements, and second dimension will be 2, that is 0 and 1. So dp of 0 and dp of I0 and dp of I1 will be there, right? Now what is dp of 0? Dp of 0 will be nothing but it will indicate the maximum beauty of the first I elements if the segment uh, ending at ith index is an even numbered segment. So dp of I0 every time will indicate the maximum beauty of the first I elements if the segment ending at the ith index is an even numbered index. Now what is this dp of I1? So dp of I1 will indicate the maximum beauty for first I elements if the segment ending at ith index is odd numbered segment. Right, so these are the two things that we need to consider, that we need to keep in mind. Now the segments, as you know, the segments can be either of even length or odd length. So I'll write this again so that you can get clarified. Now the segments that you can make, the segments can either be of even length or odd length. Right. So the next thing that you have to focus is that how will you calculate it optimally and what will be the cases that you will be considering in this particular question. So let me come down and show you up till here what I've done. You take the t test cases as an input, you take the n as an input, then you have this particular array, you take the array as an input. Once you have taken it, so you declare a dp for all the n elements of this particular array for all the I indexes, that is dp of I0 and dp of I1. That's why you have to take the second dimension, and you initialized every element of this particular 2D dp to 0, right? Initially you can take as a memset. Then what you do is, since you want to find the maximum, since for every dp of since you want to be optimal, and for every dp of I0 or dp of I1, what you want is, you want to find the maximum that you can obtain till there, right? So that's why initially you can make it as minus infinity. Every value you can make, every value of the 2D dp, every value of the cell, you can initialize it to minus infinity or something like minus 1e18, so that it is as least as possible. Then dp of 0 will be equal to 0, very basic condition. After that, what you can do is, you will start your iteration. But there are several cases that I want you to understand. Now there can be several cases in this particular question. I'll write them for you. So the cases that you have to understand is, like, they can be case 1. Let's talk about the case 1 first of all, and others cases you can easily be able to relate. So if I'll talk about the case 1, so in this particular case, what will happen is, let's say if the segment is even numbered, right? If the segment is even numbered and length is odd, right? If the segment is even numbered and the length is odd, then what will happen is, then the ith element will be multiplied by -1. Why? Because the condition that was given to us, right? The condition was that this is the thing, right? -1 to the power j plus k modulus 2 into a of I. So that is why it will happen that if the segment is even numbered, right? If the current segment that we are talking about, if it is even numbered, right? So if the segment is even numbered, if the segment is itself even numbered and the length is odd, right? So if its length is odd, so that will mean that the ith element, that is a of I, will be multiplied by -1, right? That is what you have to consider. And similarly, in this particular segment, my a of I minus 1th element will be multiplied by a +1, that is, will be multiplied by 1, and so on, it will continue. So that is what you need to understand, that if the segment is even length, even numbered, and the length is odd, then the element will be then the ith element will be multiplied by -1, and the I minus 1 element will be multiplied by 1, and so on, right? And so on, it will continue. Now there can be other cases as well. There can be other cases. The second cases also I'm explaining. So other cases I'm explaining, I'm writing it table for you guys here. So in this case, what you can consider is, you can consider this thing, that is length of the segment, that is index, You can consider this index of subarray. You can consider, and you can consider length, right? So what length of subarray or length of segment, you can say length of subarray. So what you have to do is, there can be four cases that can be possible. If the length is if the index is odd, if the index is odd is again, if the index is even, or if the index is even again, right? If the index is even and the length is, if the index is odd and the length is even, if the index is odd and the length is also odd, if the index is even and the length is even, and if the index is odd even and the length is odd, right? So these will be the four cases that you should consider, and according to these cases, like I told you for the first case, you can make the case, you can understand for the other cases as well. Now in this particular question, there is one more thing, that if you will try to generate, like in this case, if you will try to generate the segments of length n or very close to that, in that case, like you can get a TLE, because according to the constraint, if you will look, so n is given what in this particular question, if you will observe clearly, so n is given as 10 to the power 4, and there are t test cases as well, so that's why a brute force is not going to work. So if you will consider a brute force approach, so a brute force kind of approach, so it will be n cross n, that is order of n square, but it is not going to be optimal, right? So what you can do is, in this particular question, one thing that you need to observe is that the segment you will consider, right? So not consider you will not consider segment of length greater than 20, right? So the maximum length segment that you will try to consider for this particular question is going to be equal to 20, right? Great less or equal to 20. So you'll not consider any segment with the length which is greater than 20, right? And that will help you, right? Why? Because if a segment has a length of more than 10, right? In this particular question, you need to observe that if a segment that you are choosing has length of more than 10, then you can split the first half, that is the, you can split the first and the last four elements into two segments, right? Into two segments of length 2, and it won't change the sign, it will not change the sign. So this is something that you need to consider, that it does, if a segment has length of more than 10, then you can split the first half four elements into two segments of length 2, and it would change the, and it will not change the sign. So this is the intuition behind it. Now let's come back to this code and see what we are doing. So in this particular question, as I told you, like I'll be having a cost which will be having 0 and cost 0 and cost 1, sine 0 and sine 1. Now cost 0 will be what if the current segment is an even number segment. Cost 1 will be what if the current segment is odd numbered segment, right? And I'll be initializing my cost using a memset to 0. I'll mark my sign of 0 to -1. I'll mark my sign of 1 as 1. Then cost of 0 is equal to sine of 0 into a of I. Cost of 1 is equal to sine of 1 into a of I. I hope that's understandable. Now for the odd length segments, I'm running for all the odd length segments, and I'm doing what I told you, like I'll be calculating the dp of I0 and dp of I1 optimally. So dp of I0 is equal to maximum of dp of I0 comma dp of j plus j1 plus cost of 0, and similarly dp of I1 is equal to maximum of dp of I1 comma dp of j0 plus cost of 1, and I'll update my cost of 0 plus is equal to sine of 1 into a of j, right? And I'll check if my j minus 1 is greater equal to 1, then I'll again update my cost of 0, and similarly I'll do it for cost of 1. After this, once I'm done with this part, so I'll again initialize my cost to 0. I'll update my sine 0 to 1 and sine 1 to -1, because I'll now be considering for the even length segments. I'll update my cost 0 and cost 1 accordingly, and now I'll be checking for the even length segments. I'll be maximizing it for the even length segments as well. So dp of I is equal to maximum of dp of I comma dp of j plus 1 plus j cost of 0. dp of I plus 1 is equal to maximum of dp of I I1 comma dp of j0 plus cost of 1, right? After this, I'll be changing accordingly my cost of zeros. I'll be updating my cost of zeros and cost of 1. And in the end, I'll be doing what? I'll be in my dp of in the end, what will happen is, in the end, my final answers will be stored for dp of n0, that is dp of n0 and dp of n1. Both of these values will be storing the optimal answers for the length segment, as well as the for the even numbered segment, as well as the odd number segment. And in the end, I just simply need to return the maximum of these two. So I'll return the maximum of dp of n0 comma dp of n1, and that is how my question will get accepted. So this code is available to you. I've just shown it here. You can take a screenshot of it if you want. Right. Thanks a lot for watching.
Hi, and welcome to Geeks for Geeks. Today we would be discussing the problem duality task. In this problem is easy, but if you are able to break down the solution. So let us first understand what is the duality of an array. Duality of an array is the maximum length among all non-empty subsequence of the array whose GCD is greater than 1. Okay, greatest common divisor. Okay, greatest common divisor is equal to 1. Fair enough, is greater than 1, is greater than 1. Now maximum length of subsequence, not subarray, please do remember this. So what we need to do, we now know about duality. Now what we do need to know, so let us first take out the duality of an array A. Suppose this is the given array A. So all the subsequence would be first 3, then 2, then 6 and all. So you would come to the conclusion that if you consider 3 and 6, the GCD would be 3, which is greater than 1. And if you again consider 2 and 6, the GCD would be 2, which is greater than 1. Now, if you consider this is length 2. So till now we got the best answer as length 2. So if you consider all the 3, then 3 and 2 and won't have a GCD greater than 1. Okay, 3 and 2 have a GCD 1. Fair enough. This is how we need to take out the GCD. So we are given two arrays A and B. Both are of the same size. We need to consider one more array C of size n, which is initially equal to A. So initially C would be equal to A. Okay. And in one operation, you can replace any character of C with any value you want. And the thing to note is that you can do any number of operation. Okay. And this number of operation won't count to your answer. You would only count the beauty of the array C, where the beauty of the array C is defined as the number of indices where Ci is equals to Bi. The number of indices validating this will be the number of beauty of the array. Now we need to find the maximum possible beauty. So what we need to do, we need to maximize. Okay, we need to make all the values, try to make more number of values equal to B, the first thing. But we need to respect the condition that the duality of the array C should be greater than or equal to the value of the array A. Okay, so let us first solve the sample test case. Okay, so given the sample test case, this is array A, this is array B, and the duality of the array A is equals to 2. Now initially we have the C value, whose value would be initially 3, 2 and 6. So what are the numbers that are differing? Okay, so we have this number, this number, this number. So if we make this as equal to 6, then all the values would be equal to that. And the GCD of C, okay, GCD of all the values in C is equal to 3, okay, which is greater than the duality of A. So this is fulfilling the condition. So we can say that we are able to make the beauty of the array as 3, because all the 3 values are able to do that. Now, if you just try to visualize what we are doing, basically is, what we can do is, suppose the duality of the array A is equal to X and the duality of array B is equals to Y. The first thing we need to do is we need to find the duality. Why? Because we need to make it more than or equal to. To make more than or equal to, we need to take out that. So next thing what we need to do is we need to make the maximum values of C equal to B. So if if Y is greater than equal to X, then we can directly give out B as the answer, and we can say that if we assign C as equal to B, then the duality of that would be greater and it would have the maximum beauty. Fair enough? I hope this case is clear. If this case is clear, then it is quite simple. Now, what we need to do is we need to find the duality. Now, the question boils down to the fact that how to find duality. To find the duality, what we can do is we can find all the factors involved. Okay, so this is the smallest prime factor. So what we can do is, suppose it is 6, the smallest prime factor of 6 is equals to 3. So we would divide 6 by 2, which is equal to 3. So we have the factors. So it is done by the sieve method. This is just a modification of the sieve method, where we would use the sieve method to first compute the smallest prime factor of the upper limit. Okay, so that it can run for all the test cases. Okay, fair enough. Or if it was no test cases, what we can do is we can just take out the maximum value and we can find the SPF. Okay, smallest prime factor. But here we have multiple test cases, so let's generalize this thing. So we would do it on a global array, and we can calculate that. To calculate that, what we need to do is, I would just tell you, and you need to already familiar with the sieve method. Now we would make an array, and n is equals to n to the power 6, the upper limit. Okay, now we are moving forward. Initially SPF of 1 would be 1, and from 2 the SPF of that value would be equal to that value only. Initially we are doing that. Now we are saying that the SPF of all the even numbers 4, 6, 8, 10 all would have the SPF as 2. Okay, because it is the smallest. Now we start the iteration from 3, and what we do is the same sieve method. Okay, if that is equal to the same number, we are computing it. Else it is not having the same number, it means that it is already calculated, so we won't do anything. So this is just like having the previous value only. Okay, in prime factorization, this is how we would first find all the SPF. Next we move forward and we start to find the duality. How we would find the duality, I would tell you. Okay, so what we would do is we would initially have the count as 0. Initially count is equals to 0, duality is equals to 0. Now this SE is just a copy of fins. Fin is a copy of SE. Now what we would do is we would first take out this X. As I told, suppose for 6 I would take out the SPF. SPF is equals to 2. So first we would enter the SPF of 2. We would enter it. Then we would divide 6 by 2, that is equals to 3. Then we would again insert it, 3 SPF of 3. Okay, and this is what we are doing. Now after all this is done, what we are saying is, this is the, we suppose it is having 2, 3, 4, 5. Okay, not, it won't be 4. Why? Because it is not a prime number. 2, 3, 5. So what we would do is we would start hashing the values. To hash the values, we are using this. Okay, 10 to the power 6. We start hashing the values, and whatever is the largest value, we don't need to iterate again. Rather, when we are incrementing, after incrementation, we are assigning the value. Then after suppose 2 is done, we would remove it to get the first value. Then 3 is done, we would again remove it to get the first value, because there is no such indexing in the set. Okay, this is what we are doing. Now we have hashed the values. Now to find the duality of B also, we need to again unhash the values. We need to again reset its values. So instead of resetting its value, we have already the numbers that are inserted at this is also inserted at this also. So what we can do is, suppose it is 2, 3, 5. So we would take hold of the value that we have just hashed. Why to go with the whole thing? So what we are doing is, while the fence is not empty, we are making it to 0 and we are erasing it. So now fence is also reset. We can just skip the pins also. This is what we are doing. Or else you can just have a array loop, okay, and you can unhash the values. But this is more useful. Moving forward, we return the count of this. Now, as I told, we would take the input, we would take care of the queries, okay, not queries, test cases. Then after that, we would find the duality of 1 and 2. If the duality of A is less than the duality of B, we would assign every value. So the output would be n itself. All the values would be same. Else what we need to do is the duality of A minus the duality of B. Why? Because suppose the duality of A is equals to 5 and the duality of B is equals to 3. So these two values are the difference. So we need to respect that two values to make it equal. This is what we are doing. We are subtracting it and we are subtracting it from the n. Okay. So all the values would be equal, but the difference value will not be equal. This is it. Okay. So I hope things are pretty clear to you. If it is not clear, do comment it in the chat and I would make my level best to resolve it. That's it for today. Thank you and have a nice day. Hi and welcome to Geeks for Geeks. Today we would be discussing the problem count of special numbers. So before that, let us understand what is a special number. A special number is a positive integer, and what are the conditions that apply over it? The greatest common divisor, okay? The greatest common divisor of 2. So what is the first one? The first one is the quartic power of its digits. That is, suppose if it is 1, 2, then it would be 1 to the power 4 plus 2 to the power 4. Okay. And then the products of its digits, that is 1 multiplied by 2. Okay. And the GCD of both should be greater than 1. Okay. Now 1, 2, 3 is a special number and the explanation is given, so I won't be digging deep into it. Now you are given an integer and you need to count the number of special numbers x. Okay. Where? So what you need to do is you need to count the number of special numbers from 1 till less than equal to the value n. Okay. Now same goes for the number of test cases, and for each test case you would be given an integer. Now the brute force solution to this would be having a loop from 1 till n and checking each number if it is a special number or not. Now as we move forward, we would see that it is 5 multiplied with 10 to the power 8. Okay, 5 into 10 to the power 8. So in worst case, the time complexity would be 10 to the power 18. Okay, so it is not feasible because it is much greater than 10 to the power 8. So we would definitely get a TLE. Okay. Now whenever we are talking about digits, the manipulation of digits, the first thing that should come in our mind is trying every possible number and checking. So checking is not possible. So digits is there and we need to manipulate the digits. So we need to think in terms of digit DP. Okay. Now, to be honest, when I was solving this question, this problem has a clear connection with digit sum. Okay. Now, what kind of connection? That you can portray this problem as an upgraded version of digit sum at coder DP contest. Okay. The S problem that is known as digit sum. So we can see that we can go from 0 till 9 and compute all the, and 10 to the power 18, what we would do is we would have in a version of string. Okay, and we would take advantage of its ASCII value. Okay, now suppose it is digit 0, so we would subtract the value of digit 0, that would be 0. So if it is 1, character 1, then we would subtract the value of character 0, that would be 1 itself. As we increment forward, and we can do that. Now the digit ranges from 0 to 9. Okay, now one more observation is that the second part of the observation is that GCD should be greater than 1. So GCD should be greater than 1 and we are operating over the digits. Suppose the number is x, y. Suppose it is x is equal to 1, y is equal to 2. Suppose. Okay, fair enough. So 1 to 3 is a special number. We already know that. So let us see 1, 2 and 3. Okay. So we would break down the solution. Okay, 2 to the power 4 plus 3 to the power 4. And here it would be 1 multiplied with 2 multiplied with 3. Okay. Now we just don't want the GCD. Rather, what we need to do is, if we find a common factor greater than 1, then it is definitely satisfying this condition. So we can see that the multiplication is these all numbers, and after multiplication also this would be 2 multiplied by 2 into 2 into 2. So what we can do is we can say that, see, 2 is here also, 2 is here also, 3 is here also, 3 is here also, 1 is here also, 1 is here also. So we need a digit which is greater than 1 to be present at both sides. Okay, so what can be the digits that should be present in both sides? What are the options we have? So we can see that if the digit is 2, it can't be broken down to 1 because it could never be 1 into 1. Okay, because it is a prime number. Then we have 3. 3 can also be not broken down because it is also a prime number. Then 4, if the digit is 4, then it would be broken down to 2 multiplied with 2. So we won't be doing that. Now the next number is 6, that is 2 into 3. So we have already did that. Now it is 7, so we would take care of 7. Then it is 8, that is 2 to the power 3, so that is also coming here. Then we have 9, 3 to the power 3, 3 is also coming here. Then we don't have any digits, we are going from 0 till 9. So we need to handle 2, 3 and 5. Sorry, I missed the 5. Okay, sorry. So 5 can also not be broken down because it is also a prime number. So what are the digits we need to handle? We need to handle the digits 2, 3, 5 and 7. Okay. So now the states are pretty clear. Okay. This kind of tells us what is the state, and this would tell us the low and the high bound. Okay. So if it is free, then it would go from 0 to 9. If it is not free, then we need to respect the upper bound or the lower bound, whatever be our implementation. Okay, so this is just a try. You can visualize this problem as a try. Okay, so if you just talk about 1, 2, 3, then if it is represented in 1, then if it is represented in 2, then if it is represented in 3, then from 1 we have the option, we have a, so we can't go beyond, so this we have an option of 1, 2, 3, 4, then again 5, we have the option for the first index, same goes for the option of the second index. Okay, just like a knapsack problem. Okay, just like the knapsack problem. So now knapsack has a, either we take it or leave it. Here it has options of various digits. Okay, just this. Okay, let us move to the implementation so that it would be more clear, because explaining the idea of digit DP is not that much. Okay, we don't have much content to cover. Okay, you need to be well versed with the digit DP standard problems, then you would be able to easily do it. So let's talk about the implementation. So for implementation, we would first do it recursively, then we would memorize it, and that would be our solution. Okay, now there is one more thing to talk about before moving forward to the solution. Do we actually need the sum? Okay, do we actually need the sum? No, we don't need it. Why? Because we are only interested in 2, 3, 5 and 7. So we can keep the count of them if they are present or not. Or more preferably, what we can do is we can have 1, 2, 3, 4, 5, 6 and 7. Okay, instead of 7 we would have mod 7, and this would be 8 mod 7, and this would be 9 mod 7, and these all also we will be mod. This would be 1, 2, 3, 4, 5 and 6. I have not shown here you mod because uh, that would, the digit would be same, and here it would be 0, 1 and 2. So we just need a array of the state's size. We first need to be declare the size also. The size should be 2 multiplied with 3 multiplied with 5 and multiplied with 7, because it would range from 0 till 6, 0 to 4, 0 to 2, 0 to 1. This is what we need to do. And we would also have the sum. To remember the sum, if we have 7 or not, if we have 8 or not, what we would do, if we have 2 or not, what we would do, we would take use of the bit marks, and we would save it in, suppose we want to store the value 2, we would have 1 left shift 2, 1 left shift 3 to store the value. This is how we would do it. So we would also have the state as 32. Okay, fair enough. Let's move to the implementation. All the things are covered. So let us first talk about the recursive. Then we would talk about the input and all later, because we have the flow now. Okay, so if we have reached the end of the position, okay, what we would do is we would check if the sum is equals to 2 and it has 2 or not. Then we would check for 2, then we would 3, 5 and 7, same goes. And what is this? We are saving this value. We would talk about this mask function, okay, again. So this is nothing but saving the values, okay. Now, this is it. Now moving forward, we would check if the answer is already pre-computed or not. This is just a part of memorization. If it is already pre-computed, it won't be -1, so we are returning it. Else, we have started calculating it, okay? And this would be passed by reference, so that we are saving the address only, so we don't need to assign again, okay? Now, if we are tight that we have a condition that go only till this point, suppose we have a condition till 8 or suppose we have a condition till 7, so what we need to do, we need to go from 0 till 7 only. We can't cover 8 and 9 because we need to follow that path in the try. We can't go beyond that. It is still not free. So if we have a tight condition, it is still not free. So we would compute the number, we would mask it. We would talk about this util function after. Okay. Then what we would do is we would have the mod of 3, 5 and 7. Okay, this is what we are doing. If it is not having, then it is free to go in either of the direction. What we would do is we would compute the value from 0 till 9 itself. Okay, so we have a for loop from 0 to 10, and this for loop would be from the position, and we are taking care of the ASCII value. Okay, then we have the new mask, and then sum would be 0, and then we are adding each sum. Okay, we are adding that here also, we are adding that, and then we are returning. This is just a pass by reference one, so it would automatically be saved. Now let us talk about the util function and what would the dp kind. So this is what we have done: 2, 3, 5, 7 and 32 also. And then util function, what it does is, if I is equals to 0, then it would just turn on, okay, turn on the value 1, the last one. Okay, this is just turning on the value last, or is just turning, if suppose if the value is 1, okay, or 1 would be 1 only. Okay, if it is 0, 1, it would be turned on. So if it is turned on, it would be left as it is. If it is not turned on, it would be made to turn on. Now the same goes if it is 0, okay, if it is divisible by 2, then we are turning on the 1. If it is divisible by 3, then we are turning on for the second. If turning on for 5, we have done it for 3, 7, we are done. So just what I said was, I said that for 1 I am saving it to 2, then 3, this is what we are doing. But instead what we are doing is, okay, just we are mapping here, okay, sorry, here we are mapping 2 to 1, 3 to 2, 4, okay, 2, 3, 5, 2, 3 and 7 to 4. This is what we are doing to save on the space complexity, and then we are returning this. And as usual, we are making the array in the global scope, and then we are, why? Because we don't need to, because the condition is not changing, and if it is already pre-computed, why to compute it again? Okay, so then we are having memset of dp -1, and then we are having function. Okay, fair enough. Size of dp memset is nothing but sets all the values to 0 or -1. Why only 0 and -1? Because it works bit by bit. Okay, so I hope things are pretty clear to you. If you have any doubts, make sure to comment it in the comment section.